Hi everyone, this is my video number 13. On this video I'll talk on limit of the sequence. Limit of a sequence. Okay, what is limit of the sequence? I have explained to you in the previous video what is the sequence. I've explained how to find the general formula of the sequence. Now we go to the limit of the sequence. So what is limit of the sequence? Now if we consider, for example, this sequence, you consider this sequence where un is given as n over n plus 1. Okay, if you list the element of that sequence, so what you have when n equal to 1, so you have 1 over 2, right, 2 over 3, 3 over 4, 4 over 5, and so on, up to basically goes to infinite. So you can choose as big as you want. Let's say 999 over 1000, and so on. So what you can see from there, you see the difference, or this is the value of that is 0.1, sorry, 0.5. all right, and it's getting bigger. This is greater than 0.5, this is greater than that one, this is greater than that one, this is greater than 1. So basically this value is quite close to 1. Okay, quite close to 1. It's not exactly 1, but it's quite close to 1. So as n getting bigger, what you can see, this un approaches 1. Correct? You can see, and you can keep on choosing. You can keep on choosing. So for example, the denominator you can choose up to 1 million, and so on and so forth. Okay, so what I want to say here is that if we plot this or put in xy plane where this is your n, this is your un, so what you can find is that this sequence it look like that. Okay, and this is your 1, this is your 1 here, that's your 1. Okay, so each element of that sequence will not goes beyond than 1, as you can see here. So which means that as n getting bigger and bigger, this un, the element is at there, the element of un approaching 1. So this is basically the concept of limits. Okay, so the same thing for the same function there, you can always write that. I mean, if you consider 1 minus n over n plus 1, this will give you 1 over n plus 1. All right, for this kind of sequence, so what you can see as n goes to infinity, I mean getting bigger and bigger, so 1 over n plus 1, that goes to 0. Okay, so the limit in this case is 0. So all these things, it give you this limit approaches some numbers. For this limit, which one here, this limit n approaches some numbers. So we can give a formal definition of the limit, that we can write a limit of un as n goes to infinity, this is equal to some number l. So this is the definition of the limit of the sequence. So what is this? So we say this, the un is equal to that. Yeah, if and only if and only if for every epsilon positive, there exists a corresponding integer n positive such that we have un minus L less than epsilon whenever n greater than n. Okay, what does this definition means? Okay, what does this definition means? I repeat this. We say limit un is equal to L when n goes to infinity if and only if for every epsilon positive there exists a corresponding integer n positive such that the magnitude of un minus L less than epsilon whenever n greater than capital N. So in short, I can write this limit un n goes to infinity is equal to L if and only if given any epsilon positive there exists n positive such that un minus L less than epsilon for all n greater than n. Now, how can we describe this? Yeah, this definition is quite theoretical, but how can we describe this? What is epsilon? What is n, capital N? What is small n? Okay, so let me try to explain this. Let's say we have this sequence. Okay, let's say we have a that sequence, increasing sequence, and has a limit. Let's say this limit, let's say give limit, that limit, I can say, let's say this is our L. Okay, I hope you can see this. That's our L. Now, for every epsilon positive, which means we can pick up a small number of epsilon less than 1. You can choose, for example, 0.01, or you can choose even 0.1, but as long as those epsilon, as long as small number, then we can consider that. Now, if you look at this, un minus L. What is this? Un minus L. UL minus L. UL minus L means that un is here. Each of these, this is your n equal to, this is your n. Okay, so this is n equal to 1, so you have u1 here. This is n equal to 2, so you have u2 here. Okay, and so on up to n equal to n, for example, n equal to n here. All right, so we have un somewhere there. This is your un. Okay, so you can see if you take the difference between un and L, so which means we take this difference here. We take that difference. Okay, so if you consider this as an epsilon, there, if you can consider that as epsilon, if you pick up any n greater than this n, okay, this I can put in capital, let's say this capital N there. With this capital N, I can have this epsilon, okay, and then with this capital N, for any n greater than this n, you can choose n here, you can choose n here, you can choose n here. This is, for example, n plus 1 up to whatever number you want, n plus whatever, big number. The important thing is that greater than greater than this capital N. So what happened to un in this case? What happened to un? You can see that un plus 1 is basically bigger than un. So un is somewhere here. It's difficult for me because I have to hold the handphone as well as I need to write on the paper. So let's say this is your un. So you can see the dot there. So in this case your un and your n is here. Okay, your n is there. Yes, your n is there. So you can choose there as n getting bigger and bigger, un is inside, in between those two lines. In between those two lines. And this, the difference between these two lines, epsilon given. Okay, so which means if any point inside there, so of course the difference there must be less than epsilon. The difference between that with that is epsilon less than epsilon, and you keep on increase n, you know, the un getting smaller and smaller and closer to 1. All right, and the difference getting smaller and smaller and smaller, but not 0. So that's why we say it's less than epsilon. So this definition, yeah, limit un equal to L for n goes to infinity for any given epsilon, we can find this n. So in this case, this n, we can find those n. So which means in the process, we need to find what n is. There exists n such that the difference between un minus L less than epsilon for all n greater than n. You need to remember this. You need to remember this because in order to prove the limit, so we need to use this definition. Okay, so now with those explanation, I have explained to you what L is. I have explained this is un. I have explained to you what n is, capital N. I have explained to you what epsilon is. Okay, now let me recap those explanation. Given any epsilon positive, any small number, we can find an integer n such that this inequality is satisfied. Okay, and this happens when n greater than those capital N. Okay, now how to use this? So let's see some example. Let me begin with a very simple example. So let's say we want to show a limit 1 over n goes to infinity. This is 0. Okay, so this is obvious. You can see n getting bigger and bigger, so it's getting closer and closer to 0. Now, how to do this? So we begin with given epsilon positive, a small number, epsilon positive. Then from un minus L, your L in this case is 0, un is 1 over n, so this is 1 over n minus 0. Okay, which is, this is 1 over n. N cannot be negative. Yeah, this n cannot be negative, so it must be positive. So when you take the absolute value of the positive number, it gives you no change. So therefore, I can write this is just equal to 1 over n. So what we want to show? We want to show, look at the definition. We want to show that this must equal to the difference between un and L must less than epsilon. So that's what we need. That's what we need to show. So now we need to choose n, capital N. What is capital N? Now look at this. We need to show that 1 over n less than epsilon. Okay, this is what we need to show. For this, I can write 1 over epsilon less than n. Okay, then I can choose this as my n. So you can see that at any case, for any case, n is always bigger than this capital N. N is always bigger than a capital N. So therefore, I can choose. You can choose n 1 over epsilon. Thus, or therefore, you can say, thus 1 over n minus 0. This always less than epsilon for all n greater than n. So in this case, your n is this. Okay, so that's the proof. That's the proof. This is what we want to show, and we have shown that. We have shown that by choosing that n, we can have those things less than epsilon. Okay, now I said earlier that we can choose any epsilon. So what does that mean? So let's say I choose epsilon 0.01. If I choose epsilon 0.01, so our n is 1 over epsilon, which is 1 over 0.01, which is 100. Okay, now if you choose n that greater than this 100, so let's say we choose 0, 1, 0. Okay, if you choose n 0, 1, 0, which is greater than 100, which is your n or our n. Okay, if you plug in those difference, this is 1 over n, so you plug in there 1 over n, which is 1 over 101. If you use the calculator to evaluate this, definitely this one less than whatever value there, less than 0.01. Okay, the bigger n you choose, 102, 103, 100, 110, and so on. The bigger n you choose, the smaller number that you got. Still less than 0.01. Okay, so that's the concept of limit. Let me give you another example. So just a minute. Let me give you another example. So let's say we want to show that limit n over n plus 1 as n goes to infinity, this is equal to 1. Graphically, I've shown that in the at the earlier beginning of the video that this approaches 1. So this is now we prove using the definition. Okay, now given epsilon positive, remember that for the definition we have un given any epsilon, given epsilon positive, we need to find n positive such that un minus l less than epsilon for all n greater than n. This is the definition. Don't forget those things. Okay, now to prove this, given epsilon positive, so we need to show that less than epsilon. So we begin from there. So we have un minus l. This is n over n plus 1 minus 1. You can simplify this. So what you have, this is n minus n plus 1. So n minus 1 over n plus 1. That give you minus 1 over n plus 1. We take the absolute value and n is always positive. So this is, we can write this as a 1n plus n. Okay, 1n plus 1. And definitely this 1 over n plus 1, this always less than 1 over n. Okay, always less than 1 over n. This is true, right? This is true. The purpose is we want to find what n is. So for this case, I can choose. Remember that we want this less than epsilon. We want n over n less than epsilon. So I can write this as a what? 1 over epsilon less than n, n, small n. So I can choose this as my n. So we can always have n greater than this big N. Now we choose n equal to 1 over epsilon. So therefore we have 1 n over n plus 1 minus n, this less than epsilon, okay, for all n greater than n. We can always, by choosing this n, this capital N, 1 over epsilon, we can always have this. We can always have this. Alright. You might, now before that, I hope you can understand that. Unfortunately, you cannot respond directly to me now, but you might confuse a little bit. How do we choose n again here? Yeah, what make we choose n equal to 1 over epsilon? Okay, the reason is here. The reason is here. The purpose is we want to show that those here un minus l less than epsilon, and we have shown from this expression, from this working, all right, we have shown from this working that this n over n plus 1 minus 1 is less than epsilon. Less than 1 over n. Now we need to show that if we can show that this 1 over n less than epsilon, then we're done. Because the purpose is we want to show this thing, un minus l less than epsilon. So if you can show that 1 over n less than epsilon, so we're done. Okay. Now the question is, how can we choose capital N? So look at from there. What we need is this must be less than epsilon. So you just play around with that. So what you can have, n is greater than 1 over epsilon. Then you can choose n equal to this 1 over epsilon. So for any n greater than n capital, okay, those inequality will always be satisfied. Okay, so this is the proof. Now I can give you one more example. Okay, before we go to the theoretical parts. I think I still have time a little bit more. So show that the limit, okay, this is done. Show that the limit 2n plus 3 over 3n plus 2 is equal to 2 over 3. Okay, this is equal to 2 over 3. N goes to infinity. Remember that we want to prove this thing. Alright, we are not trying to find, because already given, we already have the value. To find those limits is not difficult. You can just divide by n and take n goes to infinity, then you can have 2 over 3. Now we want to show. Again, we use we use that definition. Okay, now given any epsilon positive, given any epsilon positive, then un minus L, which is 2n plus 3 over 3n plus 2 minus L, which is 2 over 3. Okay, you can simplify this. So what we have 6n plus 9 minus 6n minus 4 over 9n plus 6. Okay, and you can simplify that. That gives you 6n cancel out, so you got 5 over 9n plus 6. Okay, and always positive. Inside there is a positive, so I can write this as a 5 over 9n plus 6 without changing the equality sign there. Now from here, try to write in the single terms. Single terms. We have a single term for numerator. We have single term for the denominator. In this case, denominator we have 2 terms. So try to write that. So what you can see there, definitely this is, if you make it the denominator smaller, so you can see the right hand side is bigger. So you can have 5 over 9n, so this is bigger. Why? I think you know this thing. If a greater than b, then 1 over a is less than 1 over b. So it is obvious in this case here, 9n plus 6 is greater than 9n. So if we inverse this, 1 over 9n plus 6, this is less than 1 over 9n. You can just multiply here 5. You can multiply here 5. Alright, then we got what? The continuity that we need. Okay, now we have those inequality now. Un minus L now less than 5 over 9n. Now we need to choose. What capital N is. So how to choose? I put it here so for you to see clearly. So we want to show that 5 over 9n, this is less than epsilon. That we need to show. Okay, so from there you can always choose 5 over 9 epsilon, this is your n. So you can choose this as your n. Okay, so now we choose n equal to 5 over 9 epsilon. Alright, so therefore we have 2n plus 3 over 3n plus 2 minus 2 over 3 less than epsilon for all n greater than n. Now we're done. Okay, so I hope you understand from this. If you don't, please do the revision again and again. So I think I stop there for this video. See you in the next video. Bye bye.